Cool. So hello everyone, my name is Tanner from the Privacy and Scaling Explorations team, specifically TLS-Notary. So this is going to be just a quick overview of what I'll be talking about today. So we have the what, why, how, where, and who, and we have a couple demos to show. So the motivation behind TLS-Notary is just making all Web 2 data portable. So the current problem with Web 2 data nowadays is, say like Alice wants to prove some sort of data from her government, like say she wants to prove her identity or some banking information. Bob has no way of, if Bob's like a mortgage lender or something like that, Bob has no guarantees that the data that Bob is receiving from Alice is authentic. So I assume that most of you know what TLS is, but if you don't, it stands for Transport Layer Security. It is the S in HTTPS. It is that little green lock that you see in your browser when you go to certain websites. And it's used by, I'd say, about 98 to 99% of the internet. And this is the protocol that we leverage to have TLS-Notary work. So TLS provides authenticity, integrity, and privacy, and it is very good at that. The one thing that it is not good at is making data portable. And this is where TLS-Notary comes in. So TLS-Notary provides all of these security guarantees of TLS, but it also enables data portability. There's no trust required. There's a little caveat to that, but we'll get to that later on. And it is completely invisible to the website. The website has no idea that this is going on. So all existing data on the internet becomes composable. So why can't Bob trust Alice's data? Because of the nature of how TLS works, it uses symmetric key encryption. So Alice can go and change this data once her TLS session is complete. And unless she's really bad at Photoshop, Bob has no way of knowing if this data is authentic or not. So how can Bob trust Alice's data? Now, the best and most elegant solution would be if everyone just signed their data. Unfortunately, no one has any incentives to do this. Let me see. Yeah, it requires a cooperation from websites, but no one wants to do that. We also have OAuth, but there's issues with that as well. This also requires cooperation from websites, and it also has its own privacy, censorship, and trust issues. So this is where TLS-MPC comes in. So with TLS-Notary, we use TLS multi-party computation. So Alice and Bob have to cooperate in order to complete this TLS session. It's private in the sense that Bob only ever sees encrypted data during this process, and it's secure in the sense that Alice cannot cheat or forge any data. There is a cost, if you were here on Monday, for the secure multi-party computation talk. It is very bandwidth intensive and can take a good amount of time if your latency between the two clients is too high. So, yeah, privacy. Bob only sees encrypted information. So after the TLS-MPC session is complete, Alice can use selective disclosure and redact any information that she doesn't want Bob to know. But she can also use zero-knowledge proofs to prove statements or facts about this data without ever revealing the data itself. So maybe Alice wants to prove to Bob that she owns some identity and that she is who she says she is, but doesn't want to give Bob her address or birthday, but maybe she wants Bob to know that she does or doesn't live in the US and that she is of a certain age. So yeah, TLS-Notary solves a conceptually simple problem: how to query web servers and share the data with another party in a secure and privacy-preserving way. So how does it work? First, let's go back to TLS. So TLS currently uses elliptic curve Diffie-Hellman key exchanges. So Alice and the server exchange public keys. They do a handshake on some sort of cryptographic properties, and they generate some ephemeral session keys. Once that is done, the server and Alice can exchange ciphertext and encrypt and decrypt this data and have guarantees of the security of the data. The key exchange in TLS-MPC works quite a bit differently. If you look at the left side, nothing really changes from the server side. Actually, nothing changes on the server side. The server has no idea that this is going on. So between the server and the prover, Alice and Bob will be the prover and verifier respectively now. Nothing changes between the server and the prover or the client. The one thing that changes the most in this is we are including the verifier in this TLS session now. And so the prover and the verifier, Alice and Bob, split their TLS session keys, and so neither the prover or the verifier have the complete TLS keys. So when we get to encryption, the prover and the verifier have to cooperate in this TLS-MPC session in order to encrypt a message or like an HTTP request. The verifier, or Bob, never sees the plain text. It is completely hidden from them. The prover cannot tamper with any of the messages or try to forge any data because the prover does not know the entire TLS keys. If they try to do that, the ciphertext would be incorrect and the server would have no way of decrypting it. Then the prover also commits to this plain text during the process. Decryption, same deal. The prover and the verifier have to cooperate in order to decrypt this message, and the plain text still is hidden from the verifier. So yeah, TLS-MPC, this is just sort of like an overview of what I was just talking about. So the prover and the verifier have to jointly compute encryption and decryption with their private key shares. The verifier can never see the plain text, and the prover cannot forge a request nor the response. So only the prover communicates with the server. Like I was saying in that diagram before, the website or the server has no idea that this is going on, and that side of the exchange does not change. The only thing that's changing is we now have a third party that is cooperating in this TLS session. And I have a quick demo. So this is one we use quite often. It's the Star Wars API. So this is the prover proving to the verifier that they have some personal information about Luke Skywalker, but it's going to redact their home world. And hopefully this works. Yeah, cool. So on the left side, we have the prover, and on the right side, we have the verifier. And once this starts, so this is them setting up the circuits for the secure multi-party computation. The TLS keys are generated at this point. And we have the final result, which I'll show you a better picture of in just a second. But this is almost done. So this finishes rather quickly. This is all done locally, so it's very fast. It's normally not this fast. We're working on that. It'll be sped up quite a bit this year. And this is the end result. So let me go to the next one. So as you can see, the secret has been redacted, and Luke Skywalker's homeworld has also been redacted, but the verifier can prove or has guarantees that this data is authentic and hasn't been manipulated in any way. So use cases. There's a lot of use cases for this. Nationality is a big one. I've recently written a plugin for this for ID.me. It is I guess what the IRS uses in the US to prove your American, not really citizenship, but that you have an American identity. You can prove that you're an alumni or a veteran or anything on those websites. Say for account ownership, if you buy a Tesla, they give you a Tesla account, so you could prove that you own some physical thing with this. I keep using like the mortgage and bank example, so you can prove real world assets or your credit. There's also gaming achievements, which in Brussels last month, I think, we had a hackathon project do just that on Steam. So use cases in the wild. On Monday, if you were here for Sam's talk, you might have heard of ZK-P2P. ZK-P2P uses ZK email and TLS-Notary, depending on what you're using with ZK-P2P. We have OpenLayer and Opacity Labs. But what about reusable proofs? If I go back to the example with the mortgage lender and Alice trying to prove some banking information to a mortgage lender, what if she wants to share this information with more than just one mortgage lender? So this is where we can include a notary. So the prover or Alice can do this MPC-TLS session with a third party, which is just the notary instead of Bob. This is where that caveat comes in, because the verifier A and verifier B need to trust that this notary has not colluded with the prover. We are doing as much work on that to minimize the trust assumption as much as we can, but it is quite a difficult thing to tackle. So this is another demo using the Notary. So this is the prover proving that they own a Twitter account using the Notary. This is Hendrik. He also works for TLS-Notary, or works on TLS-Notary, his Twitter account. And yeah, we have a Google Chrome extension currently you can get on the Chrome Web Store. It just monitors for any active requests in the current tab that you're on. And this Twitter profile is an example of a plugin. So we're gonna fast forward here so that you don't see any of Hendrik's authorization keys or anything like that. No, don't steal his Twitter account. Cool, and now that's done, you can view the proof in the extension and see all of the data, everything, all of the headers are redacted by default. And you can review the response and download this as well. And we have this proof visualizer. We just actually remade this, but you can drop proofs into here, assuming that you have the correct notary key. Typically they are in the proofs or attestations themselves, but if not, like here, you just got an error because it was the wrong public key. And you can view them on these proof visualizers that we have built. And it'll show you when it was notarized and all the other information associated. I forget how long this is. Yeah, as you can see, he's proving that this is his Twitter account. Cool. So TLS-Notary in the browser, as I said, we do have a Google Chrome extension. It is on the Chrome Web Store right now. You can replay requests with it. As I said, we have just finished a plugin system. We're still working on it a little bit, but it does work. If you're interested in writing any sort of plugins, it is completely language agnostic. And basically any language that can compile to WASM, you can write a plugin with. So it's really cool. The one thing that is a little different when using the extension as well is you need to have a proxy. We have one running as well with our Notary server. Unfortunately, browsers don't allow extensions to open their own TCP connections, and so we have to use a proxy for that. So our licensing, we use the Apache or MIT. It's completely open source. If you want to use this, you can use either licensing. And I included this because I think it's very interesting. So this was originally an idea that was talked about in the Bitcoin Talk forum back in 2013, and these are all like the big important events that have gone on with TLS-Notary since. Yeah, if you're interested in building with TLS-Notary and including your project, this is a QR code for the quick start. I'll give it just a second. And these are QR codes for our Discord if you have any questions, and our Twitter if you would like to join those. Cool, and that is it for me. Thank you very much.